Yeah, it's recording. Right, okay, so step one is to transfer the program counter, because that's where everything starts, to the memory address register. Because the program counter's purpose is to hold the address of the next instruction, okay, then that's got to be the starting point for the fetch execute cycle. The memory address register, its purpose is to select, that's all it does, whatever's in there selects via the address bus a memory location that we want to access. Where that memory location is, we don't care. The CPU doesn't know whether that's RAM, ROM, or cache. That's up to the memory management system, okay? But it's just saying, oh, I'm selecting that address. You do whatever you do at the other end, the memory access controller. Okay, so that's what happens. Once we've selected a location, the control unit will issue a fetch command. So we tend to write this as main store and then say this is the location selected. So the location pointed to, so the memory address register, you can think of it as an index register to your primary store, your main memory. Okay, so we do a transfer that travels across the data bus and arrives at the memory data register. Okay, so that's 2 marks so far. If you've said that PC gets transferred to the memory address register and we fetch the contents of memory and it arrives at the memory data register. Okay, what we then do is we immediately take the value in the memory data register, because we assume at the start of the fetch that we've got an instruction. So we say, right, okay, move it to the current instruction register, because we might overwrite the memory data register when we start processing this instruction. So we take a copy. At this point, we can decode. So we can decode this instruction. So that's step 4. As soon as we've decoded the instruction, we know how far to increment the PC. So we will therefore increment the PC so that it's always pointing to the next instruction to execute. Okay. You theoretically could increment the PC further up this set of steps, but actually in a real CPU, instructions take different amounts of bytes. Okay, so you don't actually know how far to skip to the next until you do the decode operation. And you say, oh, right, I know what instruction that is now. Okay, well, you can do pre-instruction decodes and things like that, but we're trying to keep this simple. So at this point, okay, so that's step 1, 2, 3, 4, 5. Okay, step 6 involves actually loads of sub-steps, but we just write step 6 as execute. And the control unit will do whatever actions, it sounds a bit like the government, whatever it takes to execute that instruction. Okay. Right, so we execute it. So that's 6 steps of the fetch execute cycle. And if you were doing GCSE, that would have been like a really good answer, a detailed over GCSE answer for what the fetch execute cycle is. But there is one final step, and that's to check for interrupts. Because it might be we need to stop executing the current program and see if something needs attention, some device, some software that's generated an interrupt. And if we have got an interrupt, then we will have to go off and process that interrupt. Okay, it's something we still got to look at properly. Okay, so 7 marks in total. Are there any advantages of incrementing the PC? If you have an environment where all your instructions take the same amount of length, to store. So let's say we're in an ARM environment and every instruction is 64 bits long, every single instruction. Then actually, as you do that transfer to the memory address register, what you can actually do is you can actually say, send that to the memory address register, but it only works in this fixed environment. And then you can actually say also send it to the incrementer. So you can do it in parallel. So it's not a separate step. It happens as something else happens. And do that. So yeah, you could do that, but only if you have got a fixed instruction size, which unfortunately with most instruction sets, Little Man Computer's fixed instruction size, because it just uses these a core memory location, doesn't it? Because that has got the opcode is 1 digit. Oh God, I've done double P. So with LMC it would work. So the opcode is 1 digit, 0 to 9, and then we have the operand is 2 digits. So that is 0 to, I think it's 99, isn't it? So with that, you have got a fixed instruction size, so you could do the increment. You can't see that because my head's in front of that. So yeah, fixed instruction size. So we can do auto increment of PC in that setup, which I don't like Little Man Computer doing that because it's obfuscating the actual process that the control unit is going through. Right. Okay. Let's just grab that and move that out of my way. This is quite good. This little it's not bad for a bit of browser software, to be honest. I'm just going to oh, got to scroll. Oh, I've just buggered. Shouldn't have done that. Hang on. Does it let me undo? Oh, it won't let me undo the grab. No. Well, you've got it on the video anyway, which is a bit of a shame. But there you go. Right, let me just rub out that. It's in my way. Okay, yeah. So if we've got a fixed instruction set, yeah, we can pre-adjust the program counter. But there's no necessarily advantage to it. It's just, you know, the key thing is that this has to happen before we execute. Okay, that's the key. If you don't, then that will bugger everything up, because part of executing some instructions is to mess about with the program counter value, and it will break things. Okay, so you know it happens at the same time as we decode when we work out what the instruction is. Okay, so 7 marks in total for that. Right, okay, block diagram of the CPU. Tons of data to put on this. I asked you to make sure it had the registers, the components of the CPU, the buses, and the clock. Now, what I do whenever I'm drawing a diagram, I tend to follow the fetch execute cycle in my head, and I do like a loop like that for drawing the main registers. Okay, so what I'm going to do is I'm just going to do boxes to represent the registers and obviously label them. So I'm going to start off with the heart of the CPU, and I'm going to draw the control unit. Okay, so you get a mark for identifying there's a control unit, the thing that's in charge. I'm then going to do a box to represent the program counter. And you get a mark for identifying the program counter. I'm then going to do a box to represent the memory address register. So I'm going through the fetch execute cycle now. So you get a mark for that. Let me just move over a little bit. The next thing that happens there is that we connect to main memory using the address bus. So I'm going to show my memory as a big rectangle. Oh, I'm not, because that didn't do a rectangle. So I'm going to write in there main memory. Now, main memory is one of the components of the CPU. So we have to identify. If they ask you for 3 components, they are main memory, control unit, and arithmetic and logic unit. Okay, so now that we've got the memory drawn on, we can show the address bus. And it's really important to show that the address bus is one way. All it's used is for selecting. There is no information coming back to the CPU. Okay. It is a one-way bus. So far we have got 1, 2, 3, 4, 5 marks. So that takes account of step 1 in the fetch execute cycle. Now the second step was to do the fetch. So we need a register to hold the value, and that register is the memory data register, and that is connected using the data bus. So when we do that fetch, that is what the data travels from main memory to the CPU over. Okay. Right, so the next step was to say, right, we assume we've got an instruction. So what we're going to do is we're going to copy that instruction to the current instruction register. So CIR. Okay. Right, at that point, that's when we do the decode. So what we need to show on here is an incrementer. So we can decode and then do an increment. So what we tend to do is we draw another little box. Now I tend to put a plus in it. So I would just do a little box, put a plus in there, and I would show the value coming from, and I would do an arrow to show the direction, coming from the PC to the incrementer and coming back to the PC. Remember, this is just a block diagram. It's not an actual CPU diagram. Okay, so in reality, quite a lot of CPUs will do this increment by chucking, while we're still messing about with the instruction, before the arithmetic and logic unit is in use, we might pass the PC to the arithmetic and logic unit and do the increment that way. Okay, so, or some units have their own custom incrementers, just a little adder built in for the PC. Okay, so you get a mark for indicating there was an incrementer. Right, when we decoded this instruction, it may turn out that we need some arithmetic and logic help. So you will get a mark for identifying that the CPU has got an arithmetic and logic unit. That is the third component. Inside the arithmetic and logic unit is our general purpose registers. And these are used for holding temporary values. The one that we have got to know the name of is the accumulator, which we always write as ACC, because it's short for accumulator, and accumulator is really long. Okay. Right, so I've got quite a few elements on my diagram so far. Okay. But I'm still missing a few. In order for the control unit to carry out all its jobs, it needs to send signals to devices. It's one of the jobs of the control unit is to control the devices. Okay, and it does that using Oh, I've got rectangle on. Hang on. Let's turn rectangle off. It does that using a control bus. So that's how it issues all its edicts of saying you transfer this value from the program counter to the memory address register. We don't need to worry about the complications of that, but actually what's involved is things called latches and enables. Okay. So latches make information flow from a register onto the internal data bus, because all these registers are joined together. We tend to not show that. You'll see it on big, nice block diagrams. The data bus is drawn as big fat arrows, joining all the registers together. Yeah, so it issues these latch and enable commands to different components within the CPU using the control bus. Okay, and the whole thing that the control unit is governed by is a clock. So there is a clock signal that controls the whole of the fetch execute cycle. So it's what we would call in lots of mechanical systems a governor. Okay, it's the thing that controls the timing of everything. But obviously in a computer we call it a clock. It's a crystal. There's a crystal oscillator that's generating a timing signal. So we get pulses, and that kicks the control unit up the backside and says, get on with the next thing. Get on with the next thing. Okay, which is why by changing the clock speed, we increase the performance of a CPU to a certain extent. Okay, right, there is one pair of elements missing, which we don't even think about at GCSE, but is really important for us, and that is another register, which I tend to draw up here. So it's near the outside of the CPU, and it's near the ALU. This is the status register. The status register keeps track of all our arithmetic and logic outcomes. So it keeps track of when we've got a 0 value, a negative value. So one thing that you could get into the habit of writing if you ever draw this is to write those bits, the flag bits. The Z flag, which says whether a result was 0 or not. The negative flag, which tells you whether the result was negative or not. The carry flag that tells you whether a carry occurred during an operation, and the overflow flag, which we don't put as O, we put as a V, which tells you whether an overflow occurred. Doesn't correct anything. It's there for the programmer to say, right, I'll check to see if there was an overflow, and I'll do something if an overflow occurred, if I care. Sometimes you don't care about overflow and carry. You just say, right, it is what it is. It doesn't affect what I'm doing with these numbers that I'm adding up and stuff like that. Okay, so you get a mark for doing the status register. You can have bonus 4 marks if you put the flags in to the status register. And then the final mark is for showing interrupt lines. So the interrupts, the interrupt is pending, is the job of the status register. So the status register is connected externally to the interrupt lines of the CPU. Right, okay, so how many marks are we allocating for this? So let's go back through. So we'll have a mark for the PC. That's 1. We'll have a mark. Right, I'm going to do like a little picket fence thing. Tally. So a mark for the PC, mark for the control unit, mark for the memory address register, mark for the address bus, mark for main memory, a mark for the MDR, a mark for the data bus, a mark for the current instruction register, a mark for the accumulator, a mark for the arithmetic and logic unit, mark for the status register, 4 bonus marks if you did the flags, all 4 of them, so 1 for each, a mark for the interrupt lines, a mark for the incrementer, and then a final bonus mark if you did. So bonus mark is for, hang on, let me just scroll across a little bit. The bonus mark is if you showed a data bus connecting the registers, the internal data bus. The reason I want you to be aware of that isn't because you've got to necessarily show it, just so that you get in your head that data transfers from in between the registers of the CPU. So the data bus would need to be connected to, and it's a two-way bus because we can flow in either direction, the MDR, CIR, and the accumulator. But also, so this is our data bus, so label it up. But also the data bus must be connecting the program counter and the memory address register. So that's also a data bus. So just to indicate it's two-way. But also, when we do a branch instruction, so if we have like BRA in Little Man Computer and we say 50, that 50, that needs to go to the PC. Okay, let me just move my head. Okay, where we have BRA 50, that has to be transferred to the PC. So there must logically be a way for the control unit to say, take the operand and put it in the program counter. So I'm going to draw an arrow to that bit of the data bus, and no need to draw it directly to the PC, showing that we can transfer the operand, and I'm going to just write operand in there, and that's me op code, to show that that can transfer. So if you've shown the data bus internally to your diagram, then you have got a bonus mark. So it's out of 27 in total, according to my mad adding up. No, it's not 27, it's 17. Okay, so 7 marks for the fetch execute cycle, 17 marks for the block diagram. Okay, yours might not look anything like mine. It doesn't matter as long as the components are there and they're connected to the right things. So it's up to you to come up with your own. I've always done it this way because I go like in this anti-clockwise loop to do the fetch execute cycle. So I see the registers in that order. Okay. If you actually look up block diagrams for actual CPUs, so have a look at things like 6502, Z80, 6809, because they're nice, simple 8-bit processors. What you'll find is they always show you block diagrams for these things. In fact, let me just show you from a book that I've got next to me on my desk. See if I can find. Yeah, so here's a book. It's so hard doing that. Oh, it's not focusing. And there you get a block diagram. The big V thing is the accumulator, the ALU component, where it does all that, the arithmetic. I'll take a photo and put that on there, because that's the block diagram for the Z80 CPU. That's just what I've been working on, some assembly language stuff lately. Right, okay, last question we'll move on to. So let's just scroll across. I will save this image as a SVG, a scalable vector graphic, and link that into the chat when we're done as well. So you can have a video of me rambling on, which is always a pleasure, I'm sure. And just a little bit of source material raw as well. Okay. Right, okay, this final question. This is a key skill, this, ladies and gents. Being able to follow a program through. Doesn't matter what language it's in. It's in assembly language. And I gave you some further information to explain what the instructions did. So LDA 27 loads the value 27. So that's immediate addressing mode. So that gets loaded into the accumulator. Add 106 loads the value from location 106, in this case 17, adds it to the accumulator. Store 104, just like Little Man Computer does, stores the accumulator at address 104, halt, stops fetching of instructions. Doesn't stop the fetch execute cycle, it just effectively performs no operation instructions. Just sat there waiting for interrupts. Okay, which is why it's called halt and not stop. Right, so tracing algorithms. It's following an algorithm through and then trying to tell somebody how it works. So in assembly language, one of the things they might ask you to do is to say, what's the state of the registers when we've finished? So I'm going to run through this quite quick, otherwise it's going to take a while, but I'm just going to run through the fetch execute cycle. I'm just going to be the control unit. So I'm thinking like a control unit. So this program starts at 100. So what I'm going to do is I'm going to set the program counter to 100. Ideally, I should have said that and said, oh, the PC starts at 100. But you can infer it from the program we're about to execute. Right, so the memory address register ends up with 100 in it so that we can transfer the data. We do a read operation, a fetch. So the MDR temporarily as LDA 27. We know that's an instruction because we've issued the initial part of the fetch execute cycle. So we're going to transfer that to the current instruction register. We're going to decode it. And at that point, we're going to increment the PC. So all I'm doing when I'm tracing these and keeping track of these values, I'm just going to write down at the bottom of that column. So that if I ever want to know what the current state of everything is, I just look at the last value in each column. And that will tell me the state. I don't need to try and line it up, which is what you might have done at GCSE. Don't bother doing that. That's pointless. You're just making it hard work for yourself. So I've got to the decode phase. So I've incremented my PC. I'm decoding it and going, oh, load the immediate value 27 to the accumulator. So the control unit goes, hey, you know what? It's immediate. I don't need to do any more fetching. I've got my data in my operand. So the operand needs to be transferred to the accumulator from the current instruction register. So the accumulator ends up with the value 27. First instruction executed. Check for interrupts. There aren't any. Going to carry on. Program counter is already set up with the address of the next instruction. So we transfer it to the memory address register. Oh, Harriet's asked a question. It doesn't scroll this. Oh yeah, I've put 12. Well spotted. Well spotted, Harriet. I am a plank sometimes. But at least it means you're following. So that's good. Spot my mistakes and you learn something. It's a good job you'll learn a lot then with me teaching you. Right, so I've now been interrupted and I've lost my flow, but I'm just going to pick it up. So I can see by looking at this that I've done the first step of the fetch X. So I've loaded up and selected memory location 101. So I'm going to do a fetch. I'm going to bring whatever's at 101. So that's going to arrive at the memory address register. Add 106. We assume it's an instruction, so we copy it over to the current instruction register. We decode. As soon as we got it in the current instruction register, the control unit goes, right, I'm going to work out what that is. So I'm now going to increment my PC. I work out what it is. It's an add instruction. So I've got to pass control over to the arithmetic and logic unit, but I can't do that until I've got the data that I want to give it to add. So I look at my addressing mode, and my addressing mode said it's direct addressing. 106 is the address of my data. So I've actually got to fetch some data. in order to do that, I've got to copy the operand to the memory address register because I want to select memory location 106. As soon as I've selected it, the control unit can issue a fetch. So I'm fetching data now. That will arrive at the MDR. So at 106 is the value 17. As soon as that data arrives, so the control unit's fiddling its thumbs while it's waiting for slow old RAM to get on with it, which is why we have cache. All right, so it's waiting. Even with cache, the CPU's waiting a little bit. So it's waiting. As soon as that arrives, it goes, right, I can now execute this instruction. So it passes control to the arithmetic and logic unit. Says, I don't know anything about all that stuff, adding up. I just shout at things. So you get on with it. So the ALU goes, right, oh, fair enough, it's an add instruction. I'll add this value you've put in the MDR. All right, so it adds it. So it goes 17 and 27. Oh, I picked some stupid numbers there. That's 37, 41. No, it's not 41, you idiot. It's, hang on, I'll get there. 44? Right, so 44 ends up in the accumulator. 20, yeah, so I don't care. I don't care if I got that wrong. I think I've added it up right. Okay, so we've finished the fetch execute cycle, but we haven't. We've got to check for interrupts. So we check for interrupts. We're like, there are no interrupts. So carry on. So we start the fetch execute cycle again. It is not an interesting life being a control unit in a CPU. Don't ever take the job if someone offers you it. If they say, oh, just watch my job for a minute, well, let's go get yourself a burger or something, because I might not come back. A bit like what Hercules did to Atlas. When he said, just hold the earth up for a minute, mate, I'll be back. And then he never came back. Nice bloke, Hercules. Right, I'm rambling again. Okay, so we start the fetch execute cycle. 102 is in the PC, so let's transfer that to the memory address register. So can you see how much the memory address register actually changes? It shouldn't just be a list of the program counter. It depends on the instructions. Okay. Right. Okay. So 102 is in there. We then issue a fetch. So we fetch, and it arrives at the memory address register. So it's a store instruction, but we don't know that yet because we haven't decoded. Right. So we copy that to the current instruction register, because we assume when we start a fetch execute cycle, we've got an instruction. We decode. As soon as we decode, we can increment the PC. We look at it and we say, I've put CIR. Oh, dear. The joys of saying something different to what you're writing and trying to think what you're writing. That's pure multitasking, that is. Right, so we look at it and say it's a store instruction. We're writing to an address. So I've got two things I've got to do. I need to select that memory location. So I need to put 104. So the control unit is saying, right, I need to do a transfer here. I need to transfer 104 to the memory address register so that I can select that location. I also need to make sure that the value in the accumulator, which is what I'm storing, is copied to the memory data register. So 44 ends up in the memory data register. As soon as that's happened, the control unit can say, right, I can now perform, I can execute this instruction. So the 44 gets written back to memory location 104. So that 56 gets overwritten with a 44. I finished executing. The last phase of the fetch execute cycle is to check for interrupts. I check for interrupts. I can't see anything in the status register, so I carry on and I say, right, I'm going to start my next instruction. So we look at the program counter. We transfer the value to the memory address register so it selects it. We then issue a fetch command. So we get transfer from RAM across the data bus, which arrives at the memory data register. So at 103, we've got this opcode, which we've written in assembly language so we can make sense of it. We assume it's an instruction, so it ends up in the current instruction register. At that point, we've decoded it, so we increment the PC. We then look at it, and the control unit says, oh, halt. Right, I'll just stop. I'm just going to churn now, waiting for interrupts. So you get a mark if you ended up with PC as 104. You get a mark if your memory address register had 103 in it. You get a mark if the memory data register had halt in it. You get a mark if you had halt in the current instruction register. And you get a mark if you had 44 in the accumulator. So 5 marks, okay, for running through that. Obviously, you can do that quicker. I'm like explaining it out. It actually doesn't take long to just run through that instruction. Okay, so that was 5 marks. I'll just color box those final values. So that was 5 marks. So we had 5. Let's scroll back. I think that was 17. So 5 and 17 is 22. So the total for that was 29. So total 29. So add that up and you can let me know on Tuesday what you got. Assuming you haven't cheated and you've got 506 out of 29, like some of you might have. Okay, right. That's all I want to do today. The little man computer exercise I'm going to go through on Tuesday. There was 4 of those, wasn't there? These were 5. Sorry. Let me just drag them on the screen. In fact, actually, I'll just stop that recording.